So the last lecture is about the ferroelectric memories. So this is one of the emerging non-volatile memories. And this is right now a hot topic, at least in the research community. So this is the outline for today's lecture. So we will first review some basics for the ferroelectrics, from the dipoles to the polarization. And then we'll talk about some ferroelectric materials. And then we'll talk about the FeRAM versus FeFET. So first of all, what is ferro? If you recall the college physics, then there's a discussion about the dielectrics. Due to the ionized bonding between the atoms, you may have these dipoles within the material. So dipole, you know, is a displacement between the positive charge and negative charge. Then you will have this dipole pointing, let's say, this direction. So if you do not have the centralized charge, then the charge will not be neutral. I mean, then for this dipole, then you have the positive side and negative side. Then if you think about the material, then you have many of those dipoles, right? So when you apply the electric field externally, then the dipoles will be aligned along the field, right? For example, here you see that electric field, and then positive charge will push towards the right, and the negative charge will be attracted to the left. So then in the linear dielectric, the polarization actually is proportional to the electric field you applied externally. And then that is the epsilon, right? So the dielectric permittivity or dielectric constant. So here this p value is called the polarization. So that is the surface charge density. So because at the surface of the material, you will have a layer of the positive charge or layer of negative charge. So the charge density, that is like in the unit of, let's say, the microcoulomb per centimeter square. Let's say in 1 centimeter square unit area, how much charge you will have at the surface. That is called the polarization. Okay. So here, yeah, this is what I just mentioned, because in the middle of the material, all those dipoles, will cancel each other, right? So for example, here the negative charge, positive charge, they will cancel each other. Then only at the surface, you will have this net charge, right? So on this side, you have the positive charge. On the other side, you have the negative charge. So this is the typical behavior of any dielectric when you apply the electric field. So here, this is exactly what I just mentioned, right? So here, the surface, how much charge in this volume? That is the p value, okay? So the total charge divided by the area here will be the charge density. And then for the displacement field D, if you recall the EM theory, then you have the epsilon 0, which is a vacuum permittivity, and then times the electric field plus the p value, that is the epsilon times E, the electric field. So this epsilon depends on the material's property, basically due to the polarization as a surface, right? So different material have different epsilon, the relative permittivity compared to the vacuum, or we also call this dielectric constants. So here, then if you look at the category of the dielectric material, there is a subcategory. So although dielectric will respond to the field as we just discussed, but then there will be like subcategory called piezoelectric, or this pyroelectric, or within that we have the electric, ferroelectrics. Okay, so here basically the dielectric, right? We have this electric field induced polarization, and then piezo is that in addition to the electric field, you can also apply mechanical stress to induce that polarization. It's like a mechanical to electrical, like a conversion. And also this pyroelectric, you can also use temperature gradients. If you have a different temperature at two surfaces of the material, you can also create this polarization. So then ferro is a sub-category of that. This one will also have the properties like the thermal, mechanical, and electrical. But on top of that, there is one additional criterion for the ferro. That is the polarization will stay after you remove the electric field. So what is that? So when you have the normal dielectric, right? So when you have the land dipole, after you remove the electric field, those dipole will randomize by itself, right? Randomize by itself. So the net charge at the surface without field will be 0. That's a normal dielectric. So the ferro has a property that even after you remove the electric field, the dipoles will align in those directions. So you have the permanent kind of surface charge always there. So that is a ferro. Okay. So it's a special case for the dielectric. After you remove those fields, right? Right now you have the field, then dipoles are lined up. But then after you remove the field, the dipoles still stay like this. Then this, if you have this behavior, then this will be the ferro material. Okay, any questions? Okay, then let's talk about what kind of materials will show the ferro behavior. So first of all, there would be the theory to describe the ferro. So one of that theory is this Landau-Ginzburg theory. So basically here the Gibbs free energy is given by this formula in terms of the polarization. So you have this second order, fourth order, sixth order dependency. And then when you show the, let's say, the free energy, if you plot this function into this curve, you have this kind of a double wheel. This curve is exactly the same as this equation. The G as a function of the P. So the system's free energy as a function of the polarization will have this double wheel behavior. So here, if you do the derivative, let's say G over P, you will get the electric field, okay? Then if you do that, you will get this equation. If you plot that equation, it will be something like this one. Okay, so this is a P as a function of E. That is to take the derivative of this guy as a function of P. So let's talk about the ferro or energy first. So here there's a critical temperature called the Curie temperature. So above that temperature, then the ferro behavior will be gone. Even the material is ferro. For example, at room temperature, it's ferro. But above this temperature, then the ferro behavior will be gone. You can simply think that at a very high temperature, right, then those dipoles will not be aligned because of the thermal energy and so on. The dipoles will be, randomized. So you won't have the aligned dipoles. So only below the Curie temperature, then you have the aligned dipoles, then you have the ferro behavior. So here you see those are two double well in terms of the energy landscape. So those will be two stable points where you can, store the data, right? One is data one is data 0. Because the system will go to the lower energy always. So if you take the derivative of this curve, you get this kind of hysteresis in between the P and E, the electric field. We call this PE loop. And then this is like a memory hysteresis. So when you apply the field, when the field is not enough, then the P value will become positive. It's like you apply electric field, then all the dipoles, for example, the electric field towards the right, then all the dipoles will be aligned to the right. But after you remove the field, then at 0 voltage, you still have this so-called remnant polarization. So here the P value is not 0. That's a ferro behavior, right? When you reverse the field, let's say to the left, then all the dipoles will, align to the left, and then the system will switch to the other direction. But after you remove the field, then the surface will have negative PR because the other direction. So there would be this, this is like the IV curve we talked about before, right? Depending on how you draw it, right? If you sweep the E, the field will be continuous. You will have this kind of counterclockwise switching. But if you enforce the polarization value to be continuous, then you have a single S curve. And in this region, you may have some negative differential capacitance because the slope is negative. So here, if you take another derivative here, P versus E, if you take another derivative, you get a C versus V, or C versus E. Then you have the double peak like this. So that's, you take from energy, you take one derivative, energy respect to the charge, you take one derivative, you will get the polarization. Sorry, the energy respect to the, yes, to the polarization, if you take the derivative, you get the field respect to the polarization. So I didn't mention that here we rotate the X and Y. So here, this is X, this is Y. But anyway, this is after you take the one derivative, you can get this behavior. And then if you take another derivative, you get C versus E, okay? Capacitance versus voltage or versus the field. So anyway, this is the standard model for the ferro behavior. This apply well to a single domain behavior. Single domain means that the entire material, you can think is only one big dipole there, okay? Or actually they could have many small dipoles, but they all behave simultaneously, consistently. You can think this is one big dipole. If all the small dipoles respond the same way as the field change, then you can think it's a uniform, like one big dipole. If that is true, then this model is accurate, okay? But in reality, we know that there will be variations, right? This dipole and that dipole will respond differently. Then if you have that variation, then this is what really you can get from the experiments, okay? So if you measure the ferro material, usually this is what you will get. So how do you get this kind of PE loop? We will do this so-called pound measurement, positive up negative down. It's positive up, negative down. So that is this waveform. So what we are going to do is to have a two-terminal capacitor structure, right? You have two electrodes, in top electrode, bottom electrode, and in between you have the ferro material. So you apply the voltage. Let's say you ground the other one. You apply the voltage. The voltage will have this triangular waveform, right? So you have double positive sweep twice, and then you change the voltage direction to negative triangular waveform. Then what you are going to do is to measure the currents. The current will be the red one in this curve, okay, in this plot. So I will remove my sketch. So here you see the red one will be the responsive current. So why would there be current? Through a capacitor, why would there be current? Question from your fundamental, even high school physics. This is AC current, okay. This is transient because your voltage is changing, right? So then this is a transient current. So transient current, actually there are two components in this current. So what you are going to do is to integrate. So after integration, integrate current and time, you will get the charge, okay. The integration of this current, right? You have this current waveform. It's kind of complex. But if you integrate the current over time, you get a charge. That charge is this polarization. That charge is the charge that is changing at the surface, right? Because this is AC current. AC current means that you are going to have more charges at surface or less charge at the surface. So that is the p-value you are going to plot here. If you integrate from the experiments, from your measurements, if you integrate the current over time, then you get this one. So you have this kind of hysteresis. As you increase the voltage, if you start with this, then you increase the field or positive voltage, then you have this, and then you sweep back because it's a double sweep, right? So the voltage goes up, comes down. So you will have this goes up and comes down. Okay. So then actually you want to distinguish what is the real switching in the capacitor here, because the capacitor itself, even without ferro behavior, if you have a dielectric here, you have some currents due to the AC displacement currents. So you need to remove that component. So how do you do that? That is the second waveform will help you. So after you sweep the device to this positive side, you do another positive sweep. Then you will have, you repeat this one. You repeat this one. Because the device is already switched. But then when you repeat this positive sweep, you will have the displacement currents due to the normal behavior. If you have a normal capacitor, you have this part. If you're in the normal capacitor, of course, you will not starting with this point. You start with 0. So that's why here you have this part is due to the normal cap charging and discharging, or we call displacements, right? Displacements, currents. And then if you remove this portion from what you measured, then the rest is this black one. That is the real switching. That is the real switching due to the dipole flipping from one direction to another direction. So that is a real switching component of this transient current. That is a real PV loop, okay? So that's why people do this pound measurement to remove the contribution from the normal capacitors charge and discharge. Okay, so after you do that, then people call this maximum p-value, this one, as the saturation polarization. That's a maximum polarization. That means all the dipoles are flipped to one direction. You get the maximum surface charge density. And then after you remove that, then at the 0 voltage, you get the PR value. That is called remnant polarization at 0 voltage. So here, then there's also this coercive field, EC. So here, if you compare this experimental data versus the theory, here in the theory, there is a sharp transition. That is a critical field to flip the dipole, because all the dipoles will behave the same way. So they only have one number, one critical field, because above this field, all the dipoles will flip to the other direction. But in the reality, you see this transition is kind of gradual, because there are many dipoles. Different dipoles may have different critical field to flip. So that's why you have this EC is not well defined. We would say, okay, maybe somewhere in the middle. This is because there's a spread out of this EC value for different dipoles, right? For different dipoles, they may behave differently. Okay. All right. So any questions? Because the dipole and the created dipole are opposite. So that is a field that you need to apply to flip the dipole from one direction to the other direction. If you only have single dipole, then you just have a single EC. But if you have different dipoles behave differently, then you will have smooth out that. Or you have many of those, add together, then that will smooth out. So here then, as I said, if you do the small signal CV, which you take it's not exactly the same, you take the derivative from this one to this one, but in principle, that is the behavior. But the small signal CV means you are going to apply DC voltage at each step and then apply AC signal to measure the small signal response. And then if you do that, you get the small signal capacitance as a function of voltage. And typically, in the ferro, you should see this double peak behavior. Correspond to those two correspond to the coercive field, or let's say the center of that coercive field distribution. Okay. So this is how typically people characterize the ferro behavior. You need to do this pound measurement, and also you need to do the small signal CV. If you have this kind of characteristics, then you can conclude the device exhibits the ferro behavior. So then let's talk about the actual material that shows the ferro. So one of the widely used ferro material is this PZT material, lead, zirconium, zinc, tantalite. So basically PZT, right? Because lead is PR, right? Or PB, I forgot the elements. Let's start with P, okay? And then you have the zirconium and titanium, Z and T. Okay, so this material if you look at the crystal structure, so by the way, so here the ferromaterials will be a crystalline a material. It will have some crystal structure. So here, if you look at the crystal structure, so because you have three elements here, P, Z, T. So if you look at the crystal structure like this is one unit cell. So then depending on the location, I forgot which atom is this one. But anyway, you see three atoms, three colors for those three elements. But there is a one atom here. The location could have is not symmetric. The crystal structure is not symmetric. You have one atom that is above, let's say above this plane, or below this plane. Because of that atom's location, you have, because those are ionized bond between those atoms, right? The ions bonding. So you will have this built-in dipole up and down in this case, depending on that atom's location. That's the origin of this ferro behavior. From the crystal structure, in the unit cell, you have the displacement of the atom in different location that causes built-in dipole behavior. So here there are some like measurements, experiments to show the switching, and it's not uniform. You will start with some like nucleation site and then gradually flip the entire surface of the material. So this is how the actual switching may happen based on the nucleation and growth. When you apply the field, because of the variation, some of the domains will flip first, and that will create this nucleation site. And then as you further apply the voltage, then all the dipoles will flip. So there are two concepts. So when I say the dipole, there's also another word called domain. So in the ferro space. So those two are equivalent. Okay. So ferroelectric domain means this group of the material behave like one dipole. Because even within that, you may have small dipoles, but they behave the same way. So this is like a unit group that behave the same way. Electrically, this is called the domain. Okay. So one domain means a group of dipoles that flip together. But if you look at the literature, like papers or textbooks, there's another widely used term like a grain. Okay. So there's a subtle difference. Okay. So here, the dipole and domain is electrical concept. But grain is when you look at the like the TEM, SEM images, you will see the boundaries. Because the device is not uniform, you will see structurally, this is a structural concept. You will visually see the boundaries between different regions of the material. So that is called grain. So the grain may, correlate with a dipole, but there's a still debate whether this is a one-to-one mapping or no. Then this is still not well understood. Okay. So here, when we say domain, it's more like an electrical concept. Okay. It may correlate with the grain physically in the structure. Okay, so then let's talk about the ferroelectric hafnium oxide. Because right now the industry is looking into the hafnium oxide as a ferro material. That's why this topic become so popular these days. Because hafnium oxide, is already used in the manufacturing. When we talk about high-k metal gates, logic transistor, all the logic transistor below like 32 nanometer load, are all high K hafnium oxide. It's already in the foundry and manufacturing. So this PZT versus the hafnium oxide, and here both will have large polarization, more than 20 microcoulomb per centimeter square. But then they have some other differences in other parameters. For example, the epsilon dielectric constant, PZT is much higher. It's a super high K. And hafnium oxide, is like 20, 30, 40, around that. But then the EC value, the critical field, this one is lower. The PZT is lower. So if you want to maintain enough retention, you have to have very thick, because the EC is, is the voltage field is voltage divided by the thickness, the length between two electrodes. So then you have to, because this is small, you have to maintain enough voltage, because you don't want like a 0.1 voltage, 100 millivolts to switch your device. If you want the 100, let's say 1 volt to switch, then you have to make this very thick. So that's why this is not good for scaling. Okay. So the hafnium oxide EC is larger, so you can use smaller thickness to still maintain the ferro behavior. So here the hafnium oxide needs to be in this orthorhombic phase. There are many phases in the hafnium oxide. There's a monoclinic phase, M phase, we call M phase, and the tetragonal phase, T phase, and then this O phase, orthorhombic phase. Different phase means the hafnium and, because here hafnium and oxygen, the atoms, right? Not only two atoms, but then the location, the relative location of those atoms will have different possibilities. So depending on the angle, how they collect those four bonds. So there are different angles that correspond to different phases in the crystal structure. So there are different possible phases for the hafnium dioxide system. So here, normally, if you do nothing, hafnium oxide as grow will go to the other this phase, like monoclinic phase. This is because from the energy landscape, this orthorhombic phase is actually higher in the energy, in the Gibbs free energy. So the system would not tend to go to the orthorhombic phase unless you do something. Okay, so that's why initially people didn't discover the hafnium oxide as a ferro material, because other phases, like monoclinic phase, those are symmetric structure. You won't have the built-in dipole there. Only in this orthorhombic phase, there's some displacement of this atom. Therefore, you have this built-in dipole effects. Oh, okay, here, actually, I show that. So this monoclinic tetragonal orthorhombic, you can look at the crystal orientation and then figure out. So here, let me talk about the history, how this was discovered. So hafnium oxide, first of all, before I talk about this one, let me ask one simple question. So hafnium oxide already used in the high K metal gates, right? Then what's the difference there and here? Any idea?
Crystalline phases will be different. When high K it will be monoclinic and here it is orthorhombic.
Not exactly. So you need to remember this, okay? In the logic transistor, when you have high K metal gates, hafnium oxide there should not be in any of those, okay? Because there, hafnium oxide in logic, no, it's dielectric, yes, but it's amorphous. Amorphous means there's no crystal structure. If you remember phase change memory, what is amorphous, what is crystalline. In the logic, hafnium oxide needs to maintain at amorphous state phase, okay? So here, when we have the ferro must be under certain crystalline phase. That is this orthorhombic phase. So then the history was like this. Okay, in like 2006, if you recall, I talked about there's a company called Qimonda, based in Germany. That was a DRAM company, and at that time they're trying to find the high K material for the DRAM capacitor, right? You know, DRAM capacitor, we need higher and higher capacitance. So they want a higher K value. So they are trying different kinds of hafnium oxide and try to dope hafnium oxide with some other atoms. For example, add a little bit of silicon into the hafnium oxide, add a little bit zirconium or other aluminum and other elements into hafnium oxide, and then anneal that. Anneal means, you know, have some high temperature process, not really very high, maybe depends on the material. Let's say a few hundred degrees C to 1000 degrees C. Then try to anneal the hafnium oxide with those dopants. And then suddenly they see this like a double peak in the CV, because when you measure the K value, you need to measure CV, right? So in a normal capacitor, the C is just flat, right, as a function of voltage, right? The normal dielectric. Then suddenly they saw this double peak, and then they realized, okay, this might be ferro, okay, but they didn't publish that, okay. Then the company bankrupt, like in 2010, around that time, and then some researchers there then went to this NAMLab, which is a government-funded research lab in Germany, and then they continue this research there, and first published the paper in 2011 on the results at APL, Applied Physics Letter, and the IEDM conference in that year. So initially, their result is on the silicon-doped hafnium oxide. Okay, silicon-doped hafnium oxide. So here they show that actually you can measure those phases through this technique called XRD, X-ray diffraction. So if you shine the X-ray to the material because of the crystal structure, X-ray will be refracted, and then you look at the pattern. You can reconstruct the crystal orientation from the X-ray experiments. So they look at the percentage of those phases depending on the silicon dopant concentration from like 1% to like 7%. So at certain like a concentration, you see here like around 3%, then you get the most of the material in this orthorhombic phase. And then when you measure the PV, you get the ferro behavior. So again, this is PV, PE. PV and PE are similar because V and E are essentially the same. Let's say V divided by the thickness of the material is E, right? Voltage divided by the distance is a field. So let's say the PV or PE, they show this ferro behavior as we showed earlier. So if it's a pure dielectric, you have a straight line. That's why I said if you take the derivative, you get the CV. CV will be flat, right? See, it's just a slope. So anyway, so this is a dielectric ferro. So then I would say, okay, I should say the monoclinic phase corresponds to the dielectric phase. Orthorhombic phase corresponds to this ferro phase. This tetragonal phase corresponds to this so-called anti-ferroelectric phase. So the anti-ferro ideally will look like this. If it's ideal one, it's like this. At 0 voltage, it's still 0. There's no remnant polarization. So you cannot use this as a memory. But then when you increase the voltage, it does switch. So this is called anti-ferro behavior. But then at 0 voltage, it's 0. Okay, this is called anti-ferro. So the engineering challenge for hafnium oxide-based ferro is always that you play with the mixture of all those. You have to improve your process condition, try to make the orthorhombic phase the majority of the material. Okay. Then here, after that, then the research really started in the community. There are like hundreds of papers, even today, maybe thousands of papers published. So here, by doping the hafnium oxide with different dopants, you can get this ferro behavior. So here, widely used, there are two widely used. One is silicon, one is zirconium-based dopant. Okay. That's also used in the industry by those two today. Of course, in the research community, then people dope all kinds of other more exotic material. Okay. But in the industry, they prefer either silicon, zirconium, it's already in the production. So here there's an endurance behavior. How many cycles can you get this kind of hysteresis? So here, for example, typically the ferro material, if you keep cycling, there's a positive voltage, negative voltage, not enough to flip the dipole up and down. How many cycles can you do that? So you measure the PR value as a function of the cycling, right? So initially, the window, this is like the 2PR window. It's like your memory window, 2PR, the difference between those two, positive and negative. So initially, the 2PR value might be small. As you cycle the device, actually it got improved. So this is called the wake up behavior. And then at certain points, then the window will start decreasing. So basically you keep doing this cycling, and then you measure the distance here, this 2PR value, this distance, because this is positive side, this is negative side. So then after certain cycle numbers, then the device enters this fatigue phase. Okay, fatigue. Then the PR will decrease. And also, you can measure that at different temperature. At higher temperature, this fatigue will be speed up. Okay, at higher temperature. So then people are trying to understand what's the mechanism for this wake up and then fatigue. And here are some like explanations. Still, this is under active research, but one widely accepted physical mechanism is like this. So in the pristine device, initial device, because it's a mixture of those phases, and then you also have this vacancy, oxygen vacancy in the material, and you have different like dipoles or different boundaries. Then some of those dipoles are pinned at the surface due to those surface interface charges. So they are not responding to the external field. Some of the dipoles, they are pinned by the surface charge here due to the oxygen vacancy. So they're not responding. So only, for example, those two are flipping. When you do the cycling, only those two are flipping. Then you get smaller PR, right? And then after the wake up, then this oxygen is migrating due to the field. Then this pinning effect disappear. Then all the dipoles can flip up and down. So you get a larger p-value. And then if you keep doing that, then you get more and more oxygen vacancy due to the stress. You create more oxygen vacancy. Then you will get the oxygen vacancy somewhere in the middle. Then some of those dipoles will be pinned again, and they are not responding to the external cycling. So then the PR value will come down again. Okay, it's all about the oxygen vacancy, migration, generation, and so on, and the pinning effects. So here, for example, the best cycling number reported in the literature could be like 10 to the power 12. This is from a pure capacitor test even more than 10 to the power 12 have been reported. Okay. And then there's a trade-off between the PR value and then the cycling endurance. Generally, if your PR is small, every time you just flip up and down a little bit, you can keep doing that more times, right? If you flip very hard, this PR, if you use this larger voltage to flip all, then you create almost oxygen vacancy, then you do not switch too many cycles before it breaks. And also there are some other reliability effects built into the ferro. So here I show that fatigue is that when you do this PV loop or PE loop, then the PR value decrease, or this 2 PR, this window decrease. But then this is permanent, okay? Retention loss is also similar, but retention loss is without, without cycling, then the PR value tends to reduce. Then this is the retention loss. And then there's one more, which is kind of unique in the ferro. Because this fatigue is like endurance, retention is retention. We all know that in non-volatile memory, no matter RAM, phase change, whatever, you have the retention and the endurance, right? Then this imprint is kind of unique here. So the imprint means this PV or PE loop will shift horizontally. For example, here becomes this -1. Therefore, the P value will decrease. The PR value will decrease. But this only happens when you measure the other states. So here, for example, here the one state, right? Initially it's here. After the shift, then it becomes here. So the one state is still there. But then the device, if you go to the other state sense margin will decrease. Okay. So this always causes the sensing more difficult for the other states, for the imprint effects. Okay. So then let's talk about the device integration. So far, we just focus on the materials property. Then let's look at the real device, memory device. So there are two fundamental ferroelectric devices if you want to use it for memory. So one is FeFET, one is FeRAM. FeFET, ferroelectric field effect transistor. So this one is like a MOSFET. So the only difference is that here the gate stack, instead of the normal dielectric hafnium oxide, you replace that with a ferro, for example, ferro hafnium oxide. So here then you have the dipoles pointing up and pointing down. That will modulate the channel current. So you will have this IDVG curve like this, IDVG. You have hysteresis in the IDVG. So if the dipoles are pointing down, then you will have lower threshold voltage because here all the dipoles pointing down. Then you will have, let's say, the positive charge here that will easily induce the channel inversion. That corresponds to a lower VTH or low VTH, low VT. The other direction, right? You have negative charge, channel will be more in the accumulation. So by the way, here is typically NFET, N-type, okay, NFET. So that's why I have to emphasize. Typically, this is the NFET. So then the switching direction will be, this will correspond to the high VT states. So if you sweep the voltage from the low to high, 0 to high voltage, you have this counterclockwise switching. Counterclockwise. If you recall, this behavior is very similar to the charge trap NAND flash. But the only difference, remember, in the flash IDVG is clockwise. Higher voltage, you are going to increase threshold voltage in the flash. But here, higher positive voltage will decrease the threshold voltage. So this is clockwise. Counterclock. This is counterclockwise versus clockwise. Okay, that's the only difference. So that's why the program erase definition is also opposite. Okay. In the flash, programmed means you inject electrons into the gates, higher threshold voltage. So here, ferro program means you are going to make the dipoles pointing down and lower threshold voltage. Okay, just the opposite definition. And then FeRAM is 1T1C structure. So here, the capacitor, ferrocapacitor, is integrated to the drain of the normal access transistor. It's 1T1C. Or this is more like a DRAM, right? It's called FeRAM. It's not DRAM is 1T1C, but the C here is a ferro C. So here, when you have the dipoles pointing up and pointing down, then when you have large enough voltage across that, in the DRAM, we only have the displacement current. But here, on top of that, you have the ferro switching current. The dipoles flipping up and down because of charge movement. You have additional current. So that's why here, if, for example, if you apply positive voltage here, if the dipole is already pointing down, then nothing will happen, right? It's already pointing down. So when you measure the current from here, the current will be low. But if you have the dipoles pointing up, if you apply positive voltage here, this dipoles try to flip down, you will get this switching current. So that's why here you are going to see a large current from this terminal. This is how you differentiate those two memory states. Okay, this is the FeRAM. So any question? Okay, so let's look at the FeRAM first, because this one has already commercialized. This was discovered a long time back. And then the FeRAM product actually was produced by many vendors. Many of them are actually from Japan. In US, I think only TI, even TI today, Texas Instrument today has the FeRAM product. But those products are all based on PZT, the old generation of the ferro material. So here you see the history of that. You can have like a few megabytes. Not typically, yeah, as large as 1 or 2 megabytes. So this is widely used in those low cost cards, like those cards, like your hotel, a key card or something, right? So in the old days, you use this card to go to the phone station and make a phone call or something like that, or maybe this card you like transportation, like your public transportation, you swipe the card, all based on FeRAM. So this is commercially available, but then the density is not high, at most mega. Okay. So here, and in US, Cypress also produced that, but Cypress, I think, recently was acquired by which company? NXP, yeah, NXP. That means NXP also has a ferro right now, okay? So you see the like comparison, right? Let's say the FeRAM versus those are FeRAM versus the NOR flash. They're competitors. They're not competing with NAND flash because density is low. So, but compared to the NOR flash, the good thing is the write time read is similar because it's one read random access. Read is also typically less than 100 nanoseconds, but write is much faster. The ferro switching is much faster than the charge injection into the floating gates. Okay, typically less than 100 nanoseconds. And also the voltage is lower, right? So here, typically like 3 volts, you can do that switching and flash, large voltage. And then the right energy is also low because of field switching. You just pass the transient currents. And the flash, especially no flash, channel hot electron injection, the efficiency is very low. So here, you see FeRAM certainly is more competitive than the no flash for those low cost, low density application, like this card. So here, compared to the DRAM, I would say the difference here is that the destructive rate. So here, DRAM, yes, it's the destructive rate, but the write back is built in, right? Write back, if you remember, the DRAM, write back is built in by the sense amp. So here, this write back is to be more explicit. You have to do it more explicit. I will talk about that in the timing waveform. But other than that, because this is a non-volatile memory and no refresh, but then the FeRAM, if it's based on PZT, then because of scaling, as I said earlier, then it's limited to like 130 nanometer load or 90 nanometer load at most. That's why the density is low. So let me talk about the timing diagram. So that's why you understand what I'm talking about the write back. So first of all, this is destructive rate. When you read, actually you need to write it. That's a problem for the FeRAM. The reason is that, for example, here, if you want to read this data 1, you have to apply the voltage up to here. This is read voltage, the same as your write voltage. Because you want to see the switching here. If it's in the data 1, let's say this point, you want the device to switch, therefore you can generate this large current. Then you can measure it from the plate line. So you need to switch from this state to this state. This is destructive, even in the read operation. So you want to write it back. You need to bring this back. You need to follow an active write back to bring the data back. So that's why when you look at the waveform here, when you read the data 1, so first of all, the 1T1C, the word line will be turned on, which is the gate of the transistor. There's no doubt about that. But then this word line, this is plate line, this is called the bit line. So here you see the bit line is, when you read the data 1, bit line initially will be in the middle. It's like the DRAM, right? Like, oh, sorry, actually this is different. Bit line will start with 0. This is different from the DRAM. Bit line start with 0. And then due to the switching current, bit line will be charged up because the current flow in this way, bit line will be charged up. So this is the part you need to sense. Okay, you have the charging up. And then after that, plate line will be high. Plate line will be as high as your write voltage here. Plate line will be high. And after that, you need to write it back. Remember, write it back. So you always need to, in the middle, you need to reverse the polarity. Write it back means you're going to have positive voltage this side, negative voltage the other side. So you have to make the plate line low, while you need to make the bit line high to create a elective VW across this one. In the second half of the sensing, you have to play with the timing waveform a little bit to write it back. Okay. So you can analyze the waveform by yourself, and then similarly to read, I think the other one is, yeah, read data 0, that's type. So due to this destructive rate, rewrite is required. That means read also consume the cycling endurance. This is a key drawback of the FeRAM. Remember the endurance we reported before, like 1E12, 1 trillion cycles? Yes or not? But if it's every read going to consume 1 cycle, actually you cannot last for very long because read is quite often, right? If it's read and write, if write only consumes a cycle, then you can use it for some read intensive applications where you read 100 times and you write once. Then the endurance 1E12 may be okay. But here, if every read, remember the read latency is like 100 nanosecond. If you every clock cycle, if you are going to read, if the clock is here in like 10 megahertz, right, 100 nanoseconds, 10 megahertz. So 100 nanosecond, 1E12 cycles, 1E12. Then the time is not that long. So here, how much is the total lifetime? So this is 100 times 1E minus 9 times 12. 100 times 3 is 10 to the power 5. 10 to the power 5, you know, is if I recall, is 1 day, roughly 1 day. 1 in 5 seconds. If you read every clock cycle, because every read is going to write it once. Not good. But of course, for this card, right, you don't swipe swipe your card like every 100 nanosecond, right? So that's totally enough, okay, for those applications. Okay, so the write operation, I've skipped that. It's straightforward. You can follow the timing diagram. You write, basically you switch the polarity between the pelaton and bitline. Then you will going to write the data into the two directions. You have to flip the polarity between the bitline and platinum. Okay, so then some recent progress in the Hafnium oxide-based FeRAM. So Sony reported the 64 kilobits prototype at 130 nanometer at VLSI Symposium 2020. So here are some like comparison between this work with other technologies. So in their work, they demonstrated 1T1C, and this transistor is 130 nanometer transistor, and this C is a planar C, planar cap here at metal 1. And then the rate like voltage 2.5 volts, and the write latency 14 nanoseconds, and then retention they measured 85C 100 milliseconds, 10 to the power 11. So kind of okay as early work. This is a prototype chip. But one challenge to scale the technology is that you cannot use this planar cap. You have to follow the DRAM's path to make it like a cylinder, right? 1T1C, remember the DRAM? You have to have enough capacitance. In this case, you have to have enough surface area to get enough polarization charges when you flip. Otherwise, you cannot sense that current or sense that amount of charge within that 10 nanoseconds. So here, then when you scale, when you have a large transistor, 130 nanometer transistor, yes, you can have a planar cap. But if you scale to more advanced, like 28 nanometer or so, you have to make this capacitor. This now needs to be like this, right? Because this is 28 nanometer. If you want to still keep this is not to the scale, but if you want to, make it to the scale, you have to make this capacitor like cylinder. So Intel is also working on this 1T. Actually, they use 1T-NC. They just want to use one transistor, but then they have a stacked, like a vertical cap. But actually, their cap is on the side wall. They have 4 capacitors in one pillar. So they reported quite a few works in the past few years. And I know the team pretty well. And actually, the leading researcher working on this is of course, that's manager, but the leading researcher working on this is a graduate from Georgia Tech. So Professor Naimi is as a Naimi students. So he's working on this. So anyway, so this is the progress in the Intel's 1T-NC FeRAM, and their target is to make this one compatible with advanced logic platform. And I asked them how advanced is advanced. They didn't tell me. But definitely it's not like solid 130 nanometer. It will be some more advanced node. I would guess, okay. It's like Intel 7 or something like that, maybe. Yeah. And in their research, I think they use a little bit like anti-ferro, like a zirconium-rich hafnium oxide. So they try to make it more like a zirconium oxide and try to make the endurance more. And then last year, iMicron made a big announcement at IEDM, and they demonstrated the 32 gigabits FeRAM. This is the same density as today's, or at least the last year's DDR5 DRAM die density. And then they claim that they actually get close to all the DRAM spec. On top of that, they have the non-volatile behavior, right? So they get this the chip density 0.45 gigabit per centimeter per millimeter square. This is actually higher than the 1B load DRAM today. So in their demonstration, they use DRAM-like process, and build this cylinder cap. On top of the cylinder cap, they use the vertical polysilicon oxide transistor. It's like the 1T1C vertically stacked. It's not horizontal because they have to make this within this 48 nanometer pitch. The half pitch is 24 nanometer. F is 24 in this case. So they use DRAM process. We make a vertical transistor and the cylinder cap. And on top of that, they demonstrate 2 layers of this. Of course, this is layer by layer integration. It's not the 3D NAND like a cost-effective approach. But anyway, they make the 2-layer 1T1C. The reason they use polysilicon, polysilicon you can stack back-to-back compatible. You cannot use single crystalline silicon. There's no way to do 2-layer silicon like above the metal. There's no way, right? We talked about this before. Single crystalline, you need like 1000 degrees C, and you melt your metal. So you have to use polysilicon, which is fun in this case. This is a polysilicon transistor's behavior. The noise, not noise, I mean the leakage is approaching like a picoam. This is not good enough for DRAM. Because DRAM, we talked about before, due to the retention, you have to make it close to femtoam. But for the ferro, because it's not leaking, right? It's non-volatile. So you do not worry that surface charge will leak because that is ferro. Then this leakage is good enough. Okay. So then here, if you compare the timing, because they actually use the LPDDR5 like interface for the I/O, but if you look at the timing, the only like drawback compared to the DRAM is this row cycle time, the read time. Instead of 60 nanoseconds for the LPDDR5, the entire row cycle time will be a little bit longer, like 180 nanoseconds. Actually, we figure out why is that, and later I met Micron people and then I asked if that is the reason. They said yes. So the reason is that running out of time today. Can I go over a little bit for the last lecture? Yeah, okay to stay? Okay, then I can speak a little bit more because that is the trick, or not trick, I mean something, if you read the paper, you have to figure out, okay. So the reason the Micron call it NVDRAM, non-volatile DRAM. The reason the rate is a little bit slower is that the ferro, if you look at the VDD, it's 1.8 volt, if I recall, it's 1.8 volts. And if you look at the timing diagram before, you have to ramp up the entire plate line or bit line to this 1.8 volts. So the RC delay, you have to ramp up the entire bit line or plate line to be 1.8 volt. Or let's say the dynamic range, you have to sweep the wires will be 1.8 volt for this NVD run. But for the LPDDR5, if you recall the timing, the VDD is about 1.1 volts. But actually, if you recall the DRAM waveform, you are going to bias in half VDD. And you only need to sweep half VDD, which is 0.55 volts, in terms of swing of the signal on the wire. You can calculate the RC delay difference. For a wire to charge 3 times more voltage, you know it's a first order RC equation. You can look at the delay difference there. Will be more than like 3 times. If you want to charge from only 0.55 to 1.8, you're going to wait way longer time to charge up. In other words, the FE run, if you want to make it faster, you have to make the voltage lower. But even lower, you are going to operate on the full VDD instead of half VDD. Still, fundamentally, you are doubling the voltage. But if you translate to the delay, it won't be double because the exponential tail actually is more than double. Okay. Read which one? No, it's slower, right? It's slower, right? The write time is faster here. The write, TWI is the write. So TRC is, so those are, when you add up, that becomes a TRC. That's the others like TRCD is the row 2 column delay, and then TWR, the write recover, and so on. So, okay, they also reported the endurance and retention data. Looks good, actually. I will not go into the details. They published the data in this year's IRPS reliability conference. And then is a claim that they can go to like 1E15, but actually this is also projected. It's not really measured, okay? And data retention 10 years at 55 degrees C is not as good as, let's say 10 years, 85 degrees C. So this is still not the standard non-volatile memory, but it's kind of okay. All right, so the last topic, FeFET. So we already talked about the mechanism. I'll skip this slide. I just want to talk about the GlobalFoundries FeFET because this GlobalFoundries was a pioneer in this field. And the GlobalFoundries actually, because they are very close to the lab, as I mentioned earlier, so they got the technology from there and try to integrate to their platform, like 28 nanometer platform. So they use a silicon doped hafnium oxide as a gate dielectric. So just a few more words, since I already run over time, just want to say a few more words. So here, this one is good for front end of line integration with a silicon doping. Because for this one, we need 900 degrees C anneal to make it ferro. This is compatible with the front end line process because temperature is high anyway, you need to activate the dopant anyway. But for the FE run, we talked about earlier, because that is capacitor stacked on top, it's more like a back of line process. You cannot have this high temperature. So people choose hafnium zirconium oxide, where the temperature is typically 400 C for the anneal. So that's why GlobalFoundries choose this one, silicon dope hafnium oxide for the front of line compatibility, and Micron choose HZO zirconium doped hafnium oxide for the back of line compatibility. Okay, just a material choice. So here then, this is like the typical IDVG, and yeah, so this is those two curve. low VT and high VT states, and then you can keep cycling. And then you see that the cycling endurance is not that good. Okay, we'll talk about that in a minute. It's only like 10 to the power 5, 10 to the power 6. It's much lower than the FeRAM, which is 10 to the power 12. We will talk about the reasons in the next few slides. But the GF also demonstrates the array, and these are some like performance. And as I said, endurance is not that high. But today, GF actually offers the risk manufacturing of this 28 nanometer FeFET, and my lab actually is working with Global Foundry to do some design and chip design tape out through Global Foundry with 28 nanometer FeFET. I know them pretty well. We are good collaborators. And GF also migrates the FeFET to 22 nanometer FDSOI platform. And then they publish the data in IDM 2017. And they also integrate this into a 32 megabit array. And they can measure the statistics. And here the program voltage decrease a little bit compared to the 28 nanometer. And also the timing improve a little bit. But still the endurance is kind of low. So why the endurance is low? Because in the FeFET, it's not just a capacitor. It's actually the metal gate and your ferro, and then there's interfacial layer. Typically, because you have silicon channel, the interface will have a single layer of silicon dioxide. So if you look at this one versus hafnium oxide, this dielectric is lower than, the epsilon is lower than the hafnium oxide. That means the capacitance here is you have two capacitors in series, CFE and CIL. When you apply voltage here, due to the divider effect, capacitor actually is different from the resistor. The lower capacitance will get larger voltage drop. So for example, if you apply 4 volt here, let's say 3 volts drop on the interfacial layer, and 1 volt drop on your ferro. So most of the voltage drop on this interfacial layer. So that's why here the slope in the band diagram is steeper. So this high voltage drop on the single layer of silicon dioxide cause a lot of trouble because it's only a single layer of dioxide, but you get a large voltage. So you create a lot of defect, traps, oxygen vacancy. So this layer will break down first. That limits here the endurance. As you keep cycling, this layer will break down first. So that's why here the VTH keep increase because you have many traps. So you can enter this charge trapping behavior. It's more like a flash in that case because you get so many traps here, you can get the electrons. VTH goes higher. Okay. So that's a problem. This interfacial layer is always a problem in the FeFET. So here then also this interfacial layer will cause this depolarization field. Because you have some like interfacial layer, there will be some charges uncompensated at the surface, which will create a depolarization field to flip the dipoles back, even without any external field. When you have the ferro and a dielectric in between, when your ferro switches, you built in some charges in this at this surface between the ferro and the dielectric. Because you have positive charge in this here, you have some uncompensated negative charge. That charge will cause this depolarization field. It's called a depolarization field. That will also make the retention of the FeFET a problem. So it's more challenging. FeRAM is 1T1C is easier, and this one is more challenging. So here, then there's an also additional problem that right after red delay, and due to the time limitation, I will skip that. But again, this is due to this uncompensated surface charge. When you first program it, you will have attract a lot of surface charge to the interfacial layer, but that will detrap over time. Then after those charge is gone, then your ferro dipole will show up. That means when you cannot do the read right after the write right away. So there will be a delay between you do the read and write operation. So this is also another problem. And finally, for the FeFET, there will be variations because of the dipoles may not flip at the same time. Then they will have this VTH variation. So this is another challenge. And in principle, you can do multi-level operation. It's like Flash, right? You can go to the intermediate states by programming the VTH into intermediate states that correspond to some dipoles are pointing up, some dipoles are pointing down. Therefore, you can modulate the threshold voltage by changing the number of dipoles pointing up and versus pointing down. And also, industry try to move the FeFET from the front end of the line, like the global foundry, silicon channel, to the background line with oxide channel. For example, Intel demonstrated this at INDM 2020, and this year, TSMC will also present their recent result, probably with IGZO. They didn't disclose, but I know it's IGZO channel. So we are going to integrate this FeFET from the silicon channel to the oxide channel. That will give you one advantage. That is, if you have silicon and the ferro, you have the interfacial layer problem. But if you have oxide and the ferro, because ferro is also hafnium oxide, there's no interfacial layer. So that solves many of the challenges in the FeFET. That's why we have this shift from silicon in the front of the line process towards oxide channel towards the back of the line process. With this, actually, our Georgia Tech Professor Sumandata's group is a pioneer in this field. So they also will present the latest progress at this IEDM with oxide channel. I think the performance actually here is beating the TSMC and Intel's performance, at least at a single device level. All right, so then, yeah, I'll skip this one. So ferro may also find application in the 3D VLAN. If you replace the charge trapping layer with a ferro, you can also make the 3D FE land. SK Hynix is doing that. All right, so I will skip the summary and thank you for your patience for the last lecture.